Hi everybody, this is Eduardo Suarez. In this video, we're going to continue with iRVision 2D, but before I introduce today's topic, let's review for a moment what we have done so far. On one of my previous videos, I showed you how to do vision mastering. After we have done the manual mastering using the witness marks, vision mastering is going to increase the accuracy of the mastering by reducing the human error introduced by the manual mastering. Vision mastering is an automatic process done by the robot by using a camera and a calibration grid frame and taking several pictures at different angles. The process is able to improve the mastering, and as a result is going to update the master counts. Vision mastering is done when you have an application that requires high precision for the robot position, and also can be combined with a gravity compensation for those applications that have a heavy payload. A few things to notice: vision mastering is not part of iRVision. You will need a separate option package that is called IR calibration vmaster. Also, vision mastering is going to master only the robot axis J2 to J5. It doesn't master joint 1, neither joint 6. And finally, vision mastering can only be done on a 6-axis robot. Then I show you how to select the camera and lens. I show you there are 4 parameters that are interrelated: the camera sensor size, the focal length, the standoff distance, and the field of view. We saw that in conclusion, there is no a single camera that can be used as a multi-purpose camera to fit all your vision applications. Also, I show you that there are freely available lens calculators that can help you to select the proper camera and lens for your application. One other important thing is that the camera field of view dictates the size of the calibration grid that we want to use. We don't want to use a calibration grid that is going to be too big, and we don't want to use a calibration grid that is going to be too small. The size of the calibration grid needs to fit as much as possible on the field of view of the camera, and you're going to select as field of view such as is 10 to 20% bigger than the area where the part is going to be located. Then I show you how to perform an automatic calibration grid frame setting for both configurations: when the calibration grid frame is a user frame and when it is a user tool. The automatic calibration grid frame setting is a more accurate approach than using the touch-up method, since the touch-up method relies on the ability of the operator to properly teach the calibration points. Then I show you how to configure the 2D single view vision process when we have a single part in different configurations, when the part is on a table and when the part is held by the robot, and when we have a fixed mounted camera and when we have a robot mounted camera. And finally, I show you how to configure the 2D single view vision process with multiple parts of the same type and also parts of different types. We use a GPM locator tool for each one of the parts types, and also we use a model ID that identifies the part type. Finally, we also saw that when we create a web vision application, we're going to have a workflow with a set of steps that we need to follow, and that can be summarized in the following list. First, you need to have a proper mastering of the robot. Then you need to select the right camera and lens. Then you need to set the user tool and user frame. Then you are going to set your calibration grid frame. After that, you're going to configure the camera calibration. And finally, you are going to configure the vision process. On this list, we can add 2 more items: create the TP program and test it, and then do the debugging and troubleshooting. So all these are the building blocks for iRVision 2D, and they are important concepts that you need to understand when you want to move forward to more advanced topics like light tracking and RRPIC tool. So think about this list for a moment. if there are still concepts that you don't understand or you need to reinforce, I highly recommend you to look at these videos again. Now, after this introduction, we're going to talk about our today's topic. We're going to look at iRVision 2D multi-view vision process. When we have a part that is much bigger than the field of view of the camera, 2D single view process is not going to be able to give us the correct offset data for the part. In that case, we need to use more than one camera, and that is when we use multi-view vision process. So let me explain you first what the limitations are of using 2D single view vision process. Let's look at the part I have in here. Obviously, this part is much bigger than any of the two camera field of view. We're going to pick this part with the robo gripper, and we want to identify the part position, and we want to pick it up with the right offset from the reference position. If we look at this part, it has 4 holes, one at each one of the corners of the plate. The idea is that we're going to pick up the part and place it on a pallet that has 2 locator pins. So when we place the part on the pallet, it needs to be perfectly aligned with the locator pins. If we look at the part, let's imagine for a moment that we have only one camera, and the camera is looking at one of the corners of the part. So using iRVision 2D single view, we can create a GPM locator tool and teach the reference position for this hole. So what is going to happen is that the camera is going to identify the set origin for this GPM. Let's say that's going to be over here. And if we move the part from the reference position, iRVision is going to give us the offset data for the part by looking only at the information that it has. In this case, the GPM and the reference position for the part. If we only move the part on the X and Y coordinates without any rotation, we can perfectly get away by using only 2D single vision process. I'm going to tell you that again. If we move the part without any rotation, we still can use 2D single vision process, even though the camera knows just a small information about the part. Let's see how that's possible. If we have the set origin here, and we move the part this much on this direction, and this much on this direction, the new position is going to be over here. We can agree that any other point on the part is going to move by the same amount. Let's say this point over here is going to move by this much in this position and this much in this orientation. So the new point is going to be over here. And we can say exactly the same for any other part. It's going to be move this much and it's going to move this much. So the offset data that we're going to get using 2D single view is going to be a valid representation of the offset of the part as a whole from its reference position, even when the camera doesn't have any information about the other points outside the field of view of the camera. So now, the moment that we change the orientation of the part, the 2D single view vision process is no longer going to be able to give us the right offset data because it doesn't have any information about the orientation of the other points of the part outside the field of view of the camera. To fix that, we're going to add a second camera, and let's say that with the second camera, we're going to create another GPM locator tool. The second camera is going to be looking at this point in here. So now we're going to have 2 set origins instead of 1. And when we use 2D multi-view vision process, it's going to take these 2 set origins and it's going to automatically create a generic center point. So the origin is at the center of the part and not at the center of the GPM. So if we consider these 2 GPMs, the new origin is going to be over here. In the same way, if we change the position for the second camera to this point, the center point for the GPM is going to be here, and now our new generic center point for the part is going to be over here. So now, when we change the orientation of the part, the multi-view vision process will have enough information to set the offset data from the reference position. We can take this process to another level by adding more cameras. We can have up to 4 cameras in the 2D multi-view vision process. The important thing when we have more than 2 cameras is that they need to be sequentially in order, either clockwise or counterclockwise. Let's say we're going to have camera 1 over here. We can have camera 2 over here, camera 3 over here, and camera 4 over here. In the case, we're going clockwise, or if we want to go counterclockwise, we want to have camera 2 over here, camera 3 over here, and camera 4 over here. But we cannot just mix the position of the camera. Let's say we cannot have camera 1 here, camera 2 here, camera 3 here, and camera 4 over here. Just we cannot do that. It has to be either clockwise or counterclockwise. So now that we understand the principle of multi-view vision process, let's see how this is configured. We're going to have the same configuration that we had on the 2D single view vision process. Either it's going to be fixed frame offset with a fixed camera, fixed frame offset with robot-mounted camera, or tool offset with a fixed camera. The basic setting procedures are going to be the same as the 2D single view vision process, with a small difference that we're going to see in a moment. For the fixed frame offset with a fixed camera, the layout is going to be as is shown here. The part is going to be on a table, or in other words, it's not going to be held by the robot. So in this case, the offset frame and the calibration grid frames are going to be user frames, and the camera is going to be a fixed mounted cameras. For the fixed frame offset with robot mounted camera, the layout is going to be as it's shown here. The only difference is going to be that the camera is going to be held by the robot instead of being a fixed mounted camera. Notice that we have only one camera, but it's going to have 2 camera views. We're going to have camera view 1 and camera view 2. And the multi-view vision process is going to know the position of the camera views because it's going to record the position of the robot. Finally, we have the tool offset with a fixed camera. The layout is going to be as is shown here. The part is going to be held by the robot. So in this case, the offset frame and the calibration grid frame are going to be user tools instead of user frames, and the cameras are going to be fixed mounted cameras. So for the purpose of this video, I'm going to show you the procedure for the first case. That is the fixed frame offset with a fixed camera. I'm going to show you the setup procedure using the same configuration as we saw in the previous layout. Here I have the work cell. We have 2 cameras, camera 1 and camera 2. If we look at any of the cameras, we're going to have the focal length of 25 millimeters, and we're going to have a standoff distance of 900 millimeters. If we select Vision, we're going to go to Enable the Vision Simulation, and we're going to go to Vision Properties, and you're going to see here that I added a multiplexer. Notice that the multiplexer has 3 ports. On the port 1, we're going to put camera 1, and the port 2, we're going to put the camera 2. If you want to add more cameras, let's say you want to configure the multi-view vision process with 4 cameras. In that case, apparently you need to add another multiplexer. You have to come in here and here add another multiplexer, then you're going to have 3 more ports. We're going to have a user tool number 1. That's going to be the one that holds a gripper. And we're going to have 2 user frames. We're going to have user frame number 1 for the peak position from the pallet, and we're going to have another user frame for the place position on the conveyor. And then we're going to have 2 more user frames. User frame number 3, that's going to be the calibration for the camera 1, and then user frame number 4, that's going to be the calibration grid for camera 2. Just noted that for convenience, I set the same orientation for the user frame number 1 on the X direction is going to coincide with the camera 1 frame and the calibration grid frame for camera 2. We are going to open the pitch pendant. The way I did the calibration grid frame setting was using the 4-port method. We don't have enough space in here to do the automatic calibration grid frame setting because the robot is going to hit the camera frame. I'm going to show you here. Let's go to the menu, setup, frames. Here I have the tool frame number 1, and I use a tool frame number 9. That's going to be a pointer for doing the touch-up method for the calibration grid frame and also for the user frames. We're going to go to the user frames. Here is my user frame number 1, user frame number 2, and the calibration grid frame for camera 1 and camera 2. If we look at the details, we're going to see here that I use the 4-point method for the touch-up method for the calibration grid frame. And in this case, if we select coordinates and we select the user tool number 9, you want to see here that I use a pointer, and this tool frame number 9 is an arbitrary number selected for the touch-up method. We're going to select robot. We're going to go to Internet Explorer. We're going to select iRVision, and we're going to select Vision Setup. We're going to create our first camera data. We're going to call it camera 1. And we're going to select to the camera. We're going to go to Edit. And we're going to select camera setup. And on camera, we're going to select camera 1. For the row mounted camera, we're going to say no. And for the calibration, we're going to select grid pattern calibration. We're going to select the calibration setup. And over here, we're going to select application frame. We're going to select the user frame number 0. The grid spacing, in my case, is going to be 15 millimeters. And the setting calibration grid position method is going to be use frame. We're going to select calibration grid location, the calibration grid frame. We're going to select the calibration grid frame for camera 1. And we're going to take a snap. And we're going to set the calibration grid position. We're going to select calibration. We're going to select, in this case, only one plane. the projection is going to be perspective. Camera distance, we're going to change to override focal distance. And over here, we're going to select 25 millimeters. And we're going to set the first plane. We want to move the control points. We're going to press OK. And it's going to give us the calculated standoff distance of 900.1 millimeters. It's very close to what we have, 900 millimeters. We have the calibration points. And here we can see all the calibration points, and we can look at the error. The error is really very small. And we can look at the calibration result, where we're going to have the position of the camera relative to the calibration grid and the position of the calibration grid relative to the application user frame. We're going to save it, and we're going to end the edit. So now we have done the camera data for camera number 1. We need to do exactly the same procedure for camera 2. We're going to create another one, camera data. We're going to call it camera 2. We're going to select 2D camera, and we're going to repeat the same process. Camera is going to be, in this case, the second camera. For the row mounted camera, we're going to say no. And the calibration is going to be grid pattern calibration. We're going to select calibration setup. The application frame is going to be user frame number 0. The grid spacing is going to be 50 millimeters. And the setting calibration grid position method is going to be the user frame. For the calibration grid frame, we're going to select the calibration grid camera 2. That's going to be the user frame number 4. And we're going to set the calibration grid position. We're going to go to calibration. We're going to do exactly the same over here. We're going to change the camera distance to override focal distance. And we're going to set to 25 millimeters. And we're going to set the first plane. The calibration points. We're going to review all the points, and we're going to get the calibration result. So now we can save and end the edit. And with this, we have done the camera calibration for camera 1 and camera 2. If you have more than 2 cameras, you keep doing the same procedure for all the cameras that you have. Now we're going to go back to the work cell, and we can remove the calibration grids since we don't need them anymore. And now notice that we're going to have one of the camera looking at one corner of the part, and we're going to have the second camera looking at the other corner of the part. So we're going to go back to the iRVision setup, and now what we're going to do, we're going to create a multi-view vision process. I'm going to call it multi-view vision process, and we're going to press OK, and we're going to press edit. You're going to notice here that we're going to have the parent tool, and under the parent tool we're going to have the camera view 1 and the camera view 2. And each of the camera views is going to have a snap tool and a GPM locator tool. So we're going to select the parent tool. For the offset mode, we're going to select fixed frames offset. The offset frame is going to be our user frame number 1. And the image lock mode, we are not going to lock any image. Now we're going to select camera view number 1. For camera, we're going to select the first camera, camera 1. The part height, if you notice, I put the calibration grid at the same height as the part. So in this case, we're going to select 0. And now we can go to the snap tool. On the snap tool, we're going to take a snap. And we're going to set the snap window. We're going to take all the field of view of the camera because we're going to move the part later. So we're not going to make any more changes over here. And we're going to go to the GPM locator tool. We're going to train the part. So we're going to press Teach. We're going to move the control points to select this part of the window. And we're going to set the origin. For the origin, we can just move it just a little more over here. And we're going to train the training mask. We're going to mask these lines over here. Then we're going to go to the search window. We're going to make sure that we're looking at all the field of view of the camera. And for the degree of freedom, we're going to keep the orientation, we're going to keep the scale, and we're going to check the aspect ratio. So now we can save, and we can go to camera view number 2. Over here, we're going to repeat the same process. We're going to select camera number 2. We're going to set this to 0. We're going to go to the snap tool. And we're going to go to the GPM locator tool. And we're going to set the area that we're looking at on the part. We're going to set the origin. We're going to train the mask. We're going to set the search window. And for the degree of freedom, we're going to enable the orientation, the scale, and the aspect ratio. So you notice that we did exactly the same that we did for camera view number 1. In this case, if you need to add more cameras, you see that by default it's just giving us camera view 1 and camera view 2 when we select the multi-view ISO process. But if you need to add more cameras, you just select the parent tool. Make sure that you select the parent tool and not the child tools. And you just press this button, and with this you're going to add more camera views. So now we're going to go to the set data calculation, and before we press setting here, we need to press find. Make sure that you press find and you don't press snap and find. So we're going to press find. It was able to find both GPM. And now for the reference position status, we're going to press set. And here you're going to have the average reference and the average reference for X and the Y. One thing that you can notice in here, we're going to have camera 1 and camera 2, and they are not aligned, so you're going to see this is not a representation of the part as a continuous part, and that is because we didn't align the cameras in that way. The cameras are looking in other direction. But that is only a cosmetic part. The iRVision is going to be able to know that these are the two GPMs, and it knows exactly where the generic center point for the part is going to be. So now we can save and we can end the edit. One more thing that we can do, we can verify this reference position for the X and Y. We can take note of that and we can look at the part and see if this is going to be the center of the part. We're going to go back to the work cell and we're going to select the measurement tool. We're going to go from the origin of the user frame number 1, that is going to be our offset frame. We're going to go to the center of the part. And according to the multi-view vision process, we should be with the generic center point at about 550 millimeters on the X, and we're going to have 989 millimeters on the Y. So the data that we're getting from the multi-view vision process is correct. Now we're going to do one more thing. We're going to go back to iRVision and we're going to create another vision process. This time we're going to create a 2D single view vision process. And we're going to call it single view vision process. We're going to edit. We're going to select the camera. In this case, we're going to select camera 1. The number to find is going to be 1. The offset mode is going to be fixed frame offset. We're going to select as a user frame for the offset frame. It's going to be user frame number 1. We're going to go to the snap tool. We're going to take a snap. And we're going to repeat the same process again. We're going to train the GPM. We're going to set the origin. We're going to train the mask. And for the degree of freedom, we're going to select the orientation, the scale, and the aspect ratio. We're going to go to set data calculation, and we're going to put 0 for the part C height, and we're going to set the reference position. Now we're going to save, and we're going to exit. So now that we have properly set our vision process, we can just open the teach pendant and create our PP program. We're going to open the teach pendant. We're going to go to select, and we're going to select the main program that I have in here. And I'm going to show you step by step what this program is doing. We are doing exactly the same as we do every time. Just selecting the user frame number 0, the user tool number 1. We're going to go to home position. We're going to call the vision run find, and we're going to call the vision get offset, in this case using the multi-view vision process. And then we're going to set the offset on the vision register number 1, and we're going to go to label 99 if we have any errors. Then we're going to just move to the pause position, and from the pause position we're going to call the pick program. On the pick program we're going to change the user frame to user frame number 1, and then we're going to go to the approach position, the pick position. We're going to call the simulation program. We're going to wait, and we're going to go to the retreat position, and every time using the vision offset for the offset data. Then from here we're going to go to the place position, and for the place position we're going to call the program for place. In this case it's going to be exactly the same. We're going to go to user frame number 2, and we're going to go to the approach position, and the place position we're going to call the place simulation program. We're going to wait, and we're going to go back to the retreat position. And from here we're going to go back to the home position. So we're ready to run the program. We're going to run it in step mode. I already taught the position for the pick and for the place. We can look now at the vision data. You can notice here that we have an offset 0, and this is going to be the found position for camera 1 and the found position for camera 2. If you look at any of my previous videos where we have only a 2D single view vision process, you're going to see that the found position number 2 is going to show as the found position number 3 and found position number 4. That means that is uninitialized. In this case we have two positions because we have two cameras. So we're going to continue running the program. We are now in the pause position, and we're going to call the pick program. Change the user frame. I'm going to start applying now the offset from the vision register number 1. This is going to be our pick position, and what I'm going to do now, I'm going to select the user tool number 1, and I'm going to make the part visible. We're going to continue running the program. Now we're going to go to the retreat position, and you can see that the part is aligned with the reference position. So that means that we have and offset 0. And from here, we're going to go to the place position. And we're going to place it on the palette where the locator pins are. And from here, we're going to go back to the composition. Okay, the program ran as expected. We picked up the part with an offset 0. Now what we're going to do, we're going to select the part and we're going to change the position without changing the orientation. We're going to select the palette, we're going to go to part, we're going to edit the position for the part, and we're going to move it on the X direction, and we're going to move it on the Y direction, making sure that we are still inside the field of view of the camera. Let's say we want to move it to this part. So we move it almost 50 millimeters on the X and 40 millimeters on the Y. We're going to run the program again. This time we can run it in simulation mode. That's run perfectly with the right offset. We can go back to the teach pendant and see here the offset that we got from the vision register number 1. So you can think out if we change the position of the part without changing the orientation, that we should be able to apply the single view vision process and get the same result. So look at this offset for a moment, and what we're going to do, we're going to change this vision process in here, and we're going to select the single view vision process, and we're going to do the same for the get offset. Program again. Let's see what happened now. So you can see that even with the 2D single view vision process, when we only change the position without changing the orientation, we are able to pick up properly the part with its right offset. So we can go now to the teach pendant and look at the data from the teach pendant for the vision register number 1. And you're going to see here, this is going to be the offset. We have only found position number 1, and the orientation is almost 0. Now to the vision process for multi-view, and what we're going to do now, we're going to change the orientation. We're going to select the part and we're going to give it a small orientation. We're not going to go too aggressive. So now still we are inside the field of view for the cameras. and we're going to run it again. Let me see if I can pause during the run. So now we're going to pick it up, and you can see here that I pause the video. You can see here that we are taking the part with the right offset from the moved position. We're going to keep running. We're lifting the part. We're going to the retreat position. Now we're going to go to the place position. So using the multi-view vision process, when we change the part position and the orientation, we are able to get the proper offset data from the reference position. So now if we repeat the same process and we try to use single view vision process, let's see what is going to happen now. See here that the rotation was at 3.4 degrees, and we really moved the part only 3 degrees, so we have a small error. We're going to do the simulation again. And you can see that it's looking for a completely different offset. So the robot wasn't able to pick up the part properly. I go to the teach pendant and find out what was the offset that it got. It got a 109, almost minus 110 degrees, completely different from the offset that we have using multi-view vision process. In conclusion, we can say that 2D single view vision process can only be used when we are able to see the part inside the field of view of the camera. When the part is too big and it doesn't fit anymore inside the field of view of the camera, we're going to use 2D multi-view vision process. The way that 2D multi-view vision process works is that it takes the center of the GPM locator tool for each one of the cameras and creates a generic center point, and uses this center point for offsetting the data from the reference position. Similar to the single view vision process, there are 3 configurations. When the part is on the table, it's going to be a fixed frame offset, and either it can be a fixed mounted camera or a robot mounted camera. When the part is held by the robot, it's going to be tool offset, and in that case, we are going to have a fixed mounted camera. Another important point is that 2D multi-view vision process can be used with 2 cameras or up to 4 cameras. When we have more than 2 cameras, we have to make sure that they are sequentially in order, either clockwise or counterclockwise. Finally, I'm going to leave the link to the work cell on the description below, and thank you for watching.